Okay, so our second speaker this morning is George Papas, who will talk on the p-adic, values of functions.
Thank you for the invitation. And perhaps the most curious property of this talk is that the previous speaker gave a better version of it, since so much is based on his work. So let me start with my motivation of studying this stuff, which was Zilber-Pink for curves. Which says that if X is a Shimura variety, and V for S is some irreducible curve not contained in a proper special sub, then if we look at the atypical locus of S, which is the union over all special subvarieties of codimension at least 2, and we look at all the intersections with S, then at least the expectation is that this is a finite set. So progress here has been slow, I think. When X, instead of Shimura varieties, when X is GM to the N, this is known by work of Moran and Bobbieri-Massesani. And then when X is an abelian variety, this is known by Heidegger plus Deal. And in the Shimura setting, all of the partial results that we have to this day by Nord, David, and I have some work here as well, fall under the following general picture. So we have some curve inside H bar, or here this is the p-adic or some compactification, I believe, in David's work. This is the toroidal compactification of AG. And then if we assume this curve is defined by Q bar and S bar intersects the boundary H bar AG in some sort of an aggressive way. Yeah. Then some part of Zilber-Pink holds for the actual curve inside HZ itself. So a variant of this problem is the following. So we have some curve, again the same, rotation defined over some number k, together with an isolated point on it. So I want to isolate an S0 point, and then we look at the following picture where we have some family over S bar of semi-abelian varieties, and we assume that over the complement of the isolated point is an actual family of abelian varieties. And X over S0 is not an abelian variety. Then what is actually proven in these cases that we have so far is that there exist finitely many points in the bar such that the endomorphism algebra over the bar again is unlikely large. Or by unlikely, I mean it is sense of unlikely intersection in the moduli space. Okay. So the key input on the arithmetic side, which is all I'll be talking about, is this observation by Chris Martin, that it's enough in this setting to show that if the endomorphism algebra is large, then the height, sorry, the corresponding point is bounded from above by the degree of the extension to some power. And this is used by Chris and Martin to show that if this is true, then if the endomorphism algebra is large, again, then QSQ is large. So we have enough gamma conjugates. The point S0 here corresponds to some intersection with the boundary, and in Y1 to the n, which Chris talked about on Tuesday, if I have a curve inside here, then S will intersect the boundary. But in Shimura varieties like AG, no longer the case. Because we have projective curves inside AG. So what I wanted to take a look at is this sort of more direct approach to this problem, is that if I just have family of abelian varieties, one parameter. Of principally polarized abelian varieties, what can we say about the height of points with again endomorphism algebra that is unlikely large?
And can you express unlikely large? Just in terms of X over S?
Sorry, one more thing?
Can you express unlikely large?
Yes.
Without the word unlikely.
Fair point. So in general, we assume that the family is generic, or in other words, that if I have a family like that, I get a morphism from S to AG. And I want IS, this is an assumption I'm making throughout, is that this has its image post-generic curve. Or in other words, the image is not contained in a proper special child. And at this point, as long as G is greater than or equal to 3, every extra endomorphism is applied because of the dimension of the special subvarieties that define extra endomorphisms in higher dimensions. In G, when G is equal to 2, we have to be a bit more careful. I'll be talking about that. In A2, we want to count the set of intersections because I remind you that the dimension of this Shimura variety is just 3. And hereby, if we look at the set where the dimension of y is 0, then this is finite by André-Oort, which I believe in this case is due to Zilber-Pink 24. And this smaller dimension, so when G is just 2, we have a very concrete description of the special subvarieties that show up when we're trying to count this set. So we know that Y, in this case, will be of either of three types. So the first is curves parameterizing Euclidean surfaces with complex multiplication. The second one is curves parameterizing abelian surfaces again. All of this is the same. Isogenous to the square of the same elliptic curve. And since we're not looking at the André-Oort problem, we can assume without CM. And the third type of curve that shows up is curves parameterizing the abelian surfaces, isogenous to two elliptic curves, only one of which has CM. And Rees and Martin have sort of introduced this convenient vocabulary here that we call this QM curves, these square curves, and E cross CM curves. And if Y is any of these three, I will call a point that lies here by the same acronym. So a QM point is a point of intersection with a solvent. Right? So with Zilber-Pink in mind, this variant 2 over there can be sort of upgraded. So f of x to s as before, a one parameter family of principally polarized abelian surfaces. And I can assume that I'm also given number 2. And I can also assume that I'm given an S naught, which is also star point. So where star can be any of those three acronyms. And so the question becomes if S is another such star point of the same type, then I would like to have bounded that looks like this. Times. So all of the
Can you say again, what is the start point?
no, just being lazy. Star is any of those three.
Any,
Yeah. If I have a QM point, I want to count other QM points around it.
Sure.
Yeah.
Also indicate how one finishes the argument. If you establish this height bound, is there also a bound in the degree of such points, QM points or star points?
Yeah, good question. All right, so the catchphrase here is that Masser and Woodholz have these either isogeny estimates or endomorphism estimates that give you something that looks like something that you can associate to special curve in this case is bounded above by the max of QSQ, then the fourthing side of XS to some power. And then the point is that this value height very much comparable to fourthing side, so you can really replace it. And at the end of the day, you get that if you had something, you would have the degree over here is bounded from below by something that only depends on the special subvariety that you're intersecting with. So you have enough. What do I want to? And just like Chris talked about on Tuesday, the crucial height bounds come from this method of André-Oort in G functions, which I'm not assuming you remember everything about, so I'll reintroduce them. And first of all, how do they connect to our picture here? And this is again to if we're given this pair that comes up over there of our family of abelian varieties and an isolated point of interest, then if we look at a local parameter, so we can find matrix of power series that are G functions that we can naturally associate this picture. And they pop out as solutions to the differential module we get by looking at the relative theorem with the Gauss function. The functions themselves.
So it's,
Yep.
now it's a family of abelian surfaces.
Yep.
That's why you have GL4.
Yeah. Otherwise, it's GL2G. So,
Zero is no longer arithmetic.
huh?
Yes, zero is not, the point is.
Yeah,
it's no longer-
yeah. G functions themselves were introduced, I believe, by Ziegler in the 20s, you see? 19. Ziegler did the following definition, showcase a fixed number field, and I'm looking at power series, coefficients in K. And if I'm given a place in K, I'll write iota V for the corresponding embedding into CP or C, and I write iota V of Y for corresponding power series in CVX. And Ziegler gave the following definition. So Y is Z function if it satisfies the following three properties. First of all, it's a solution to a linear homogeneous differential equation with coefficients in AS. Two, if we look at Archimedean places, this power series defines a converges, so it's an actual proportion. So analytic function at 0 and 3. That the coefficients of my G function have sort of not too large denominators, so precise. Wait, what? Okay. Definition is this. K or M less than this. And so I forgot the n is bounded by C to the n for some fixed C. So if we're given a family of G functions, we want to look at polynomials in A, let's say, and plug in our G functions at some point psi. As Chris talked about. If we're given some sign to power. And of course, what I wrote over there makes no sense by itself because I have power series and I'm plugging in a psi. So, yeah. And the point is that we'll call such relations, and this is due to André, the terminology here, global if they make sense. They hold. for all V, or it makes sense to look at them. So for all V here, for which psi V is within the radius of convergence, minimum of one, and R V left.
This is totally Hungarian.
Linear. And non-trivial if we can't find some polynomial R tilde inside 2 bar x1 to xn, or we've thrown in little x, such that on the functional level we have a 0, and if we look at this R tilde and we specialize the coefficients to our point of interest, we recover the original polynomial. So in other words, a relation is global if it holds whenever it should, and it's non-trivial if it's not coming from some sort of functional level where we've specialized. And the key tool we use is as the principle for values of G functions. That says if I'm given some G functions as before, and I look at this set of Q bar points, for which I can find a non-trivial and global relation among the values of the family psi of degree B homogeneous. Yeah, homogeneous, but non-trivial. No, homogeneous, sorry. Then we can bound the height psi by the degree to some power. That is effective.
And T is delta.
Yeah. Thank you. So we have some family of G functions that we've associated to the pair of the family plus the point. And the game that we play is that we try to find global non-trivial relations. And I'll introduce some notation first. So if I'm given values, so if I'm given some point where I'm interested, that I'm interested in, and some place W in the extension, then I will say S is W-adically close to a central point S naught if I mean precisely the case where I have to find relations. W of the family weight. And throughout here, I have fixed the pair that I had before, where I have some family principal polarized abelian surfaces and some point of interest. And K is my fixed number. So sort of the first step in all of this is that if S and S naught are W-adically close, then we define some polynomial RSW.
A big S or a little S?
Bit less. So depending on the point. Roughly speaking, with coefficients in KS. Such that, first of all, if I plug in the G functions at psi, I want this to be 0. And I want my SW to be non-trivial in the above sense. Oh, and throughout are both sorry, S and S naught are both the same star type. So both QM, both squared, or both equociated. And there's a moreover part. If W, sorry, the central fiber over S naught does not have supersingular reduction of W, then the polynomial we create, so this RSW, does not depend on W. And here I forgot that my W is either Archimedean or place or place of finite place of good reduction for the central fiber X. Yes. Question?
When you say it does not depend on the W, you mean for the finite place or also for the
Only for those finite places that don't have super singular reduction. But for the Archimedean, they still depend. So this problem itself, I believe, or in another setting, was considered by André and Georgios, where we have a family of elliptic curves instead of surfaces. And then S and S naught are CM points. And if memory serves me right, feel free to correct me here. André describes RSV when V is a super singular prime. Or ES naught, and then Georgios is due to André. And Georgios BEQ. No. BEQ. Sorry. Hopefully I didn't misspell this. For all by finite element. Using different methods.
in this case, I think only the super singular.
Yes. Yeah.
That's a lot.
Yes. As long as you don't have the same CM field. As long as you don't have the same CM field. Or S and S naught. But that's the interesting here.
If it is ordinary, you have the theory of a lifting, so you have basically only one S of reduction.
I'm a little confused. In the statement of the lemma, what's the hypothesis on the C over evaluating the Y?
One more time.
You have the assumption is about an S and an S naught, but there's a conclusion about it C.
Thank you.
You mean reason to your argument? Oh, yes, there are some exceptions if the order is not the same.
Yes.
CM field, but not the same.
Yeah. Yeah, and just as we talked about, so the way we make sense of p-adic values of G functions is that we have in a small enough disk embedded in the curve, we have an isomorphism between sections and flat sections tensor of it, and then
Look, can I ask quickly about the lemma also? You say the relation doesn't depend on the place W. What does that mean exactly?
okay, so you get some polynomial which will have some coefficients. The coefficients don't depend on that. If you have non-supersingular.
But presumably you could do that even with supersingular reduction. It's just you would have no control over the degree, right? Presumably that in and of itself is not the problem.
The degree is the same.
Sorry.
The degree is the same in all, pretty much. It's like 4. So you got a degree 4 polynomial. The point is, how do the coefficients depend on the place? Because you might get a different polynomial, same degree.
Yeah.
One might have 5, the other one.
But am I right to assume that, say, as my Archimedean place varies, I'm probably taking a product of relations over the
Yeah, sure.
Yeah.
Sure.
So RSW maybe does depend on W if W is Archimedean.
Yeah. Only not super single. Finite. Yeah. Or super, yeah, or Archimedean. Yeah, thank you. But the problematic ones are defined.
Yeah, great. Yeah, just thanks. That clarifies.
Yeah, so just like Chris talked about here, we have on the one hand this isomorphism between sections over the disk with flat sections over the disk, and then on the other hand, flat sections again over a disk. We can naturally identify this with some homology, perhaps the CV here, of the fiber where I'm being extra lazy here, and I just write that. This is just dating or singular homology of the analytification in Q, or crystalline homology of X naught when I look at the mode W over some ring like that. And then I want to tensor with KFW, to be precise. So again, that's just like we talked about, if we fix some basis of sections of H1 around in some affine open neighborhood of a slot, and we fix some basis of H1 B slot, then we get some period matrix that expresses this basis in terms of this basis, and my G functions are related to this matrix in the following way. And now the idea is that, oh, sorry, I forgot to mention. Here, this is due to Bertha August, 82, and August 83 for ramified places. And now the idea is that if we have some sort of extra endomorphism, and we get the following commutative diagram, so we get cells, tensor something here, lazy, pull back in the Tarango homology, and then if we look at the pullback in the respective p-adic homology, which we have associated with, sorry, not associated, identified with via choosing the basis with the cohomology of the central fiber. Then we can translate having extra endomorphisms to relations among the periods. So this would look something like the extra endomorphism times the period matrix at S is the period matrix at S times the matrix we get by looking at how the pullback acts on crystalline cohomology. And then we come back to G functions to recover something that looks like this. And we can even isolate the G functions in this picture to something that looks like here I'm looking at the RAM YT is periods at 0 times the action of the extra endomorphism on crystalline or Betty, and then I've multiplied by the inverse here. And then the point of this lemma is that if you choose this basis in sort of a nice way and really embrace your OCD, you can find relations here, which at the end of the day will not depend on V or W. Apologize for the change in notation if we're not super singular or okay. And sort of the punchline. Oh, I erased what I want to do. Nice. Nice. Well, the punchline is that if I'm given some star point of interest, then I really have to look at Archimedean places by themselves. Super singular places of proximity by themselves, and then I get some polynomial that deals with everything else. And I want to bound the degree of this because by this for the Archimedean contribution by something that looks like C naught prime times what I will introduce in a moment as supersingular places of proximity of S and S naught times K is Q. Plus a third constant that just comes out of this part. And not contained in a proper special subbarite or just quotes generic. That also contains certain star point of interest for which X S naught has everywhere potentially good reduction. And if we look at the set star points for which the set of problematic primes, so supersingular primes of proximity, is bounded by N. Is finite.
Star points to the same type.
Yes. I've got a couple of minutes. It's a really full question. Oh, and at least in my head, I think this can be viewed as saying that naively, 1 over S minus S naught is S integer or rather N integer where the sense of like OK S integers and usual notation. Well, I've used too many S's, but the usual notation is S integers.
Questions?
Can you say something about this number? Singular, because already the this is there is this process again, but
Yeah, the,
estimate.
so for the Brouwer-Ziegel version of this problem, the height bound can be made very explicit, and the problematic set of primes where I'll be a bit of an awful person and just change this to J invariant. This is the set of primes in M for which P doesn't divide the discriminant associated to J times the discriminant associated to J naught. And I can find an M that looks like this is x squared. And moreover, this here is 1 for all primes L not equal to P, where this is the Hilbert symbol. I would like to conjecture that we can bound this by something that looks like this. To something smaller than 8. I think that would be enough for effective Brauer-Ziegel. The discriminant corresponding to
this formula one sees that cardinality of the set is approximately the square root of discriminant. So not 1/8.
Yeah, there's no way. Yeah, that's my point.
Other questions? I wanted to ask, you talked about embracing your OCD.
Yeah.
Can you say something about the source of the independent relation? Or I guess you did suspect it, that you were going to find one.
We noticed like I was playing around with this stuff with Chris and in our joint project, and for ordinary primes, that there was no dependence. And then the point in higher dimensions, I feel like this should be everywhere. But for ordinary primes, you can really choose the basis well to sort of count, keep count with opinions. So yeah, that simplifies the period error.
I just quickly, this everywhere potentially good reduction, that's probably not serious, right?
I expect so, but
It's just you didn't deal with bad faith at this point.
but for QM stuff, it doesn't even show up.
Right.
Okay, let's thank George.